this next video is going to focus in on the effects of catalysts and what the catalysts do. And what are the differences in catalysts that you can have. Well, the first thing I'm going to definitely focus in on is when you hear the word catalyst, its sole number one function would be to lower the activation energy necessary to have that chemical reaction. So what a catalyst does, let's take a look at these potential energy diagrams where you see energy that's your reactants and products have. Your reactants start on the left of the potential energy diagram, your products are on the right. And when you break their bonds, what you generate is this thing called the activated complex or the intermediate. Those are vocabulary words we use all the time. So in a chemical reaction, all chemical reactions have potential energy diagrams, and these are examples of potential energy diagrams. Your reactants start on the left, your products are on the right. So the amount of energy that the potential energy stored in your products would be here in this diagram, and the amount of potential energy stored in your reactants are here. And you can see from the potential energy diagram on the left that the products have less potential energy stored in them than the original reactants. So therefore, if you do this reaction, it's going to be exothermic. So if the products have less potential energy than the original reactants, you have an exothermic reaction. Fact, in order for you to have a chemical reaction, you're going to have to break the bonds. To break bonds, that's an endothermic process. You got to put energy in to break bonds. See, the amount of energy it takes to get from here to this point up here, this is referred to as your activated complex. This is what you have when you take your reactants, you break their bonds. You have a very highly unstable chemical, which is referred to as an active. It's not really a chemical, it's a bunch of pieces of fragmented atoms. And the fragmented atoms are your activated complex. So you're left with a situation where you have a highly unstable substance. And the unstable substance will immediately rearrange itself to become stable. And by doing that, you create new bonds. When you create new bonds are formed. Therefore, you're becoming more stable. That's always an exothermic process. The question is, how exothermic would determine whether you're going to end up with a overall exothermic reaction or endothermic reaction. Because whether something is exothermic or endothermic, it's a comparison of the potential energy. So if you compare the potential energy of your products minus the potential energy of your reactants, and you get a negative number, that means you got yourself an exothermic reaction. But breaking bonds is always endothermic, and making bonds is always exothermic. If you want to know overall what you got to compare your bonds and your products minus your reactants. But what a catalyst would do is immediately affect the height of that activation energy. Symbolism, universal symbolism for activation energy is E with a little sub A. So the height of this peak a catalyst will immediately lower that number. Because what you're going to do is you're going to generate an alternative mechanism step. Another way to get to your product. You're going to create a different type of activated complex. This activated complex would be over here if you have a catalyst. Now there actually is chemicals that you might want to slow down a chemical process. Well, chemicals that slow down a chemical process create also a different type of activated complex with more potential energy in them than an original activated complex for the reaction without this chemical. Chemicals that slow down a chemical process are called inhibitors. And that would be an important role. Let's say you're studying cancer. Obviously, you would slow down that reaction. So you would generate inhibitors instead of catalysts. You would use inhibitors because you want to slow down the reaction. So the reaction on the left is an example of a exothermic reaction. And the one on the right is an example of an endothermic one. Because here you can see the potential energy of your reactants are down here. And the potential energy of your products are up here. So the products at the end have more potential energy in this reaction. Therefore, it's an endothermic reaction. So the difference of the potential energies we told you in class if no work energy is being done, is directly related to this thing called the delta H of the reaction, the enthalpy of the reaction. And the enthalpy of the reaction is on a molar basis. So you can see an example of exothermic and endothermic. But again, what a catalyst will do, even for an endothermic reaction, is lower this peak. So the activation energy originally for this reaction was how far it would get the reactants from this point to the top of its peak, which is right here. This is your activated complex. But by adding a catalyst, you lower that value to this new point. So therefore, it's going to be easier to get the reaction to go with less activation energy. So at the same temperature, if you're supplying a certain amount of energy, the reaction is going to go faster with the catalyst. Now, when you're dealing with catalysts, you should be aware that there are different types of catalysts. There is what we call homogeneous catalysts, and there are heterogeneous catalysts. But before I get into that, let's just look at a typical AP simple free response question. Here's 4 diagrams of potential energy diagrams. And it says identify 2 diagrams that could represent a catalyzed and an uncatalyzed reaction for the same reaction. How would you know that they would be for the same reaction? Well, if it's the same reaction, therefore you have the same reactants, the reactant would have to have the same amount of potential energy. So the 2 diagrams, the diagrams that have reactants with a certain amount of potential, they all have, you notice they all start at the same place, right? But your products of the same reaction should also have the same amount of potential energy. So these 2 here, the products have the same amount of potential energy. And these 2 reactions represent an exothermic reaction because the products have less potential energy than the original reactants. The only difference between these 2 reactions is the height of this peak. This one here and this one here. This is the reaction without a catalyst, and this is one with a catalyst because the height of the peak has gone down. That's a typical type of question you would see related to potential energy diagrams. Now, a demonstration that I'm going to show you in class, if we have enough, no more snow days, would be an example of the combustion of methanol in the presence of what we call a heterogeneous catalyst. Now, what does that mean, heterogeneous versus homogeneous catalyst? Okay, a heterogeneous catalyst is a catalyst that's not in the same phase as your reactants. So we all know that methanol is highly explosive and combustible, especially that methanol vapor. If you react with oxygen, you're going to get CO2 and water. We all know that. And all you need is an activation energy that a match can supply, which is a lot, believe it or not, in the world of chemistry. A match is a lot of energy. But I say that you could perform the same reaction at room temperature with no match. And all you would need is you have your methanol and you have your oxygen. But all you would need is a catalyst. And this is an example of a catalyst. One of the most famous catalysts that are heterogeneous are transition metals. Transition metals are awesome catalysts. Why? Because they have, as metals, they have high electronegativity. So on the surface of the metal, they're able to draw electrons. So if you have a lot of bonds, you're going to be very sticky to the surface of a platinum metal. So if you have a piece of platinum and you have reactants that have a lot of bonds, like organic molecules, those bonds will be attracted to the surface of the platinum. So at the surface of the platinum, what will happen is the reactants will align correctly for for an effective collision. So in the presence of platinum, if I put platinum in this chemical reaction, this combustion reaction, this explosion can take place at room temperature. And we're going to show you this in class as a demonstration of how catalysts can easily reduce the activation energy for a reaction even like the combustion of methanol, so that it would combust at room temperature in the presence of the platinum wire.